So suppose we have a model, and this is going to be our tree with its particular topology, with its branch lengths, and its branch lengths are going to be in some way proportional to the clock rate. And so we could start off, say, if we think of the clock rate, start off with an idea of what the clock rate is. And so this could be different values of the clock rate here, and this could be different values of the likelihood score of the tree given the sequences. We start off there, and okay, we choose a tree and we measure a value. And obviously what we want to do is we want to maximize the likelihood. So we keep changing the parameter, likelihood keeps going up, that's great. Oh, gone too far, let's go back a bit, and we find the maximum. That's excellent. However, the real problem, and as you'll see later, is there's actually very many parameters and very many submodels, and just scanning parameters like that isn't really going to work. Really, because there's so many combinations, so many parameters and so many combinations of parameters that in fact you haven't got that nice simple shape. You've got these terribly complicated shapes in multi-dimensions. So if you started at one place, thought you found the peak just by going up all the time, in actual fact, you wouldn't have done. And really, when you're looking through the parameter space to find the good set of parameters, you'd have to go down a bit before you could go up to find the real peak. So, rather than just, as before, having this idea of this hill climbing algorithm where you change your parameter, and if it's better, you go, okay, that's good, I'll have that parameter, now I'll just try to find better one, better one, better one. In fact, you use a thing called Markov Chain Monte Carlo. And this is really where you say, okay, I'm going to change the parameters, and if the parameter gives me a better score for the tree, then I will accept those parameters and get that better likelihood. But if it gives me a worse answer, I will sometimes accept it, because sometimes you have to go down before you can go up to find that true optima. Sometimes, in this case, actually it itself has an algorithm. And in this case, sometimes means that you accept the worst move with a probability proportional to the ratio of the new and the original likelihood times the priors. So I'll just flick back to show you. So, if I can do that. Yes, this part. So you calculate the ratio of the original to the new of these. Let me. And there's actually very good mathematical reasons for this. You can show that it is a good thing to do, but don't worry, I won't go through the maths today. But the outcome of this is that what you end up doing is trying different parameter values, sometimes accepting good ones, sometimes accepting slightly worse ones, and you try and try and try many times. In fact, you do it several thousand times. This is all within the program, of course. For example, 1 million times, 10 million times, in fact, is typical. And what happens is that you start off and you have an initial climb up the hill, and then you kind of reach a plateau where you're kind of hopping about the set of good values. And it's really those set of good values, they're the ones that you're going to say, okay, well, these comprise my set of answers. These are the ones I'm going to take the average of and find the standard deviation of to give me the average parameter values. So one of the outputs of BEAST is it's a log file, and what you get, so this is all the different steps along the bottom, 10 million steps along the bottom. These are all the different likelihood values here. And what you see is at the start, you can just see it climbs up and then it reaches a kind of plateau. So typically, you run the algorithm and you throw away the first 10% and keep the remaining 90% because these are the good answers. And so each of these points is associated a posterior here, a prior, a likelihood, and several other parameters, including this one here, which is actually the clock rate. And if we just look at the good ones, so this now is our estimate of the clock rate. Again, it's about 5 in 1,000 in a year. And we can see that, so we've got our mean of our estimate and we've got a distribution which has a standard deviation. So this is our answer for our clock rate. This is our Bayesian answer for our clock rate. BEAST also, of course, gives you the actual trees. And what it does is for each of those good samples, you get a tree. So you're going to get a file with 10,000 trees in it. What you can do, though, is out of those good samples, you can choose the best one, the one with the highest posterior of those samples. It's not necessarily the absolute best tree in the whole universe, but it's the best one out of those samples. And that's called the maximum clade credibility tree. And on this tree, what you do is then you look at all the other trees and you say, okay, well, the branch lengths, because remember the branch length is a parameter that's going to change as well. The branch lengths of all the other trees are slightly different to this tree, but I can put confidence intervals on where they are. So this is my tree. This is now a time scale along the bottom. This is not genetic distance, this is a time scale. So we've made a time-scaled tree. And these blue bars here, those are the confidence intervals for the nodes, the internal nodes of the tree.